Hello and welcome to the iSystem webinar series. Today's episode, the first one in 2021, is about remote debug control and automation using Python. You will learn about the various features of the iSystem API called isystem.connect and how you can remote control the blue box with various Python scripts. By the way, the API is included in every WinIdea download with various samples for getting started easily. My name is Sabrina Kisslinger. I am the moderator today. The speaker is Alesh Koshir, who will lead you through the technical presentation. Alesh is Field Application Engineer at iSystem and is responsible for customer support and training. In his previous engagements, he worked as an embedded software engineer developing CPU applications and automated testing using C, C++, C#, MATLAB, and Python. Before we start, I would like to give you some general information. During the webinar, you will be muted. For questions, please use the Question tab. The webinar slides can be downloaded below the Question tab in the Handout tab. Today's episode will be recorded and published on the iSystem webinar YouTube channel. At the end of the webinar, we will pick some questions and these will be answered by Alesh. All questions we cannot answer directly will be answered afterward by email. And last but not least, please check your audio settings. You may need to adjust your PC audio settings to the source you are using. So in general, the audio settings of this webinar platform need to be the same as set in your local PC. So that's it from my side. I'll hand over to Alesh. And here we go.
Thanks, Sabrina, for the introduction. Welcome to our webinar. I will be presenting remote debug control and test automation using Python. After this webinar, you will be able to oversee the potential and possibilities of iSystem Connect Automation API. You will be able to start scripting right away using the interface. You can access online material and start reusing example scripts. Let's check what is the agenda for today. First on the agenda is an introduction of iSystem scripting. I will describe a hardware and a software setup used for the automation of the iSystem tools. Then I will present the most used classes of the iSystem Connect API. After a certain class presentation, I will demonstrate it with a live demo. I will start with Connection Manager. Next on the list are Debug Facade, Loader Controller, IDE Controller, Address Controller, Data Controller, Execution and Breakpoint Controller. Last on the list will be Coverage Controller. In the end, I will present the iSystem Connect documentation and online example scripts. Let's start. A real target CPU is always used with the iSystem automation setup. A target is connected with a debug and sometimes with an optional trace cable to the iSystem debugger. WinIdea, that is a debugging IDE, contains the session configuration used by a automation script. Besides iSystem Connect, you can also use isystem.test and isystem.fnet APIs. These are the automation APIs for testing and automation of the fnet add-on modules like CANLIN module and analog digital I/O module. The iSystem software package also includes the test idea, that is a test tool. Today I will present only the iSystem Connect API. It is a module that automates the iSystem debugger with a nickname Bluebox. The iSystem Connect automation script can be used for the automated debugging, automated testing, and in the production when the blue box automation is needed. Several programming languages are supported: Python, Java, C#, MATLAB. The C++ language is also supported, but the C++ classes are limited in functionality and the API is rudimentary. After downloading an isystem.connect SDK, you get the installer, several examples, and the documentation. iSystem provides the online documentation with examples. Then isystem.connect is added to installed Python as a side package. On the side, you can see an example of the C# script. You can access an iSystem Blue Box over an Ethernet connection. Also, a configuration when scripts are executed on a remote PC host while an iSystem Blue Box is connected to a local PC where both PCs are connected over the Ethernet network is supported by the isystem connect. WinIDEA can execute the Python script as a child process. There can be more than one script executed in a batch mode at the same time. WinIDEA doesn't interact with these processes, except when we exit WinIDEA, then all of script child processes are terminated too. Let's go to the live demonstration where I will demonstrate how to run Python script with a WinIDEA. I have prepared Cortex-M WinIDEA session and I will demonstrate how we can create a Python script from the scratch within WinIDEA IDE. So I will open File, New. This will create a new file. I will select Python script. Then I will also add basic imports. Basic imports already import isystem connect API, creates several instances of controllers. I will delete what is not needed right now, that the screen will be simpler and more, it will be easier for you to understand what I'm doing. So here we import isystem connect and we create a connection manager and we opened the last open WinIDEA session. This is it will open my project which that I'm using right now. Then I create a debug controller. This is a instance of debug facade. This class has many features that we can use for the debugging. So I will type another line just to show you how to start. Let's say I will add also a line. I will use a code completion that is also added inside WinIDEA, and I will add run until the function. Let's say we will run after downloading flashing. We will run a program until the main function. Okay, because this is non-blocking, I will also add another line, debug controller, wait until stop. This so the script will wait until this function will be hit. Okay, I will save a script. Let's say first script, it will be Python script. Okay, save it. Then the script is selected. I can run it from WinIDEA. I will run script and wait. So we see the flashing has started, initialization started. Okay, flashing, and now the execution run until the main function. I will close the console. The connection manager creates a connection to the WinIDEA session. It can establish a remote or a local connection. A script is executed on a remote PC in the case of remote connection, while WinIDEA is installed and Blue Box is attached to local PC. With the connection manager, you can open and connect to the last open and used WinIDEA session, or you can select a specific WinIDEA session by your choice and open WinIDEA and connect to it. With the connection manager, you are able to check the connection status and you disconnect at the end of the script. Connection to multi-core CPU that have many WinIDEA sessions, one per each CPU core, is handled with the multi-core connection manager class. I will demonstrate a remote connection example. I will execute a Python script on a remote CPU that will connect to WinIDEA session on the local PC. The remote script will then control the blue box connected to the local CPU. It is important that the version of the isystem.connect always match exactly the WinIDEA version used for the automation. First, I will check if the WinIDEA has enabled Ethernet access for the scripting. I will open Tools, Options, and here it's checked the enable isystem.connect over the TCP IP. For the TCP connection, the port 5315 can be used. Okay. My WinIDEA build version is 9.17.184. So I will check this with the script. Next, I can check my IP address of the local PC. So my local IP address is this. Okay. Next, I will intentionally disconnect my debugger and WinIDEA just for the demonstration purposes, that you'll see that my remote script works well. So next I can connect to my remote PC. Okay, connect. First, this I will check. Okay, my local IP. You see, it's a different PC with a different IP address. I can check with a ping whether my connection to my local PC works well. 64. Okay, it works. So I can present you my remote connection Python script. In the first line, I will import isystem.connect. Then I will create an instance of connection manager. And in the next line, I will print out my isystem.connect version. Then I will connect exactly to my local PC with the IP 172.29.10.64, and I will use my port 5315. Then I will create a debug facade. I will flash the binary that is defined in WinIDEA. I will run until target init function, and at the end of the script I will disconnect. So I will use Windows prompt command. I will use a Python. My Python I will directly call the script by using Windows prompt. So let's go. I will go to local. Okay, here my local. You see, it runs until the target init, and the WinIDEA is connected. So I can go back to my remote PC. Uh, the script finished without any exception. So I can return back to my presentation. As already said, the multi-core connection manager establishes a connection to multi-core CPUs. Primary WinIDEA instance operates the debugging of the primary core. First, the connection to primary WinIDEA instance is established. Then, connection to additional WinIDEA instances of the secondary cores can be established. Before connecting, the IDs of each CPU core must be known. I will demonstrate the multi-core connection with the Aurix second generation target. I will switch to the demonstration. So let us first look into the script, into the multi-core connection Python script. At the beginning, I have a definition of the primary core ID. This is CPU 0, and the secondary core ID is CPU 1. The CPU target is TC397XA. It has 6 secondary cores, but for this script I will open just primary and the core and this one set of the secondary cores. At the beginning, I will also open from the scratch the WinIDEA session. This line I, I explicitly define what project, what WinIDEA session should be opened, and then after the connection to the primary core, the debug facade for the CPU number 0 is established, then connection to the secondary core and debug facade 1 is created that controls the secondary core, and then both cores will start running. After a couple of seconds, the disconnection to the secondary core is executed, and then the primary core is disconnected too. So let's go to WinIDEA command prompt. Here I will run the multi-core connection script. So the WinIDEA is opened from the scratch. The right session is opened for the TC397XA. The downloading is executed, and now the secondary WinIDEA session will be opened, and the debug symbols are downloaded, and both core runs, and the script is disconnecting. Okay, I will close both WinIDEA sessions, and I will check. Yeah, the multi-core connection script finished without any exceptions. The debug facade contains some functionality of the several controllers needed for typical debug case. It contains functionality of the loader controller, execution controller, data controller, breakpoint controller, address controller. While debugging, you need to create an instance of debug facade, and you can have a powerful tool for the automation on disposal. You don't need to create several instances of different classes for that. I have demonstrated many times the most basic feature of the loader controller, that is download of the binary defined in WinIDEA session configuration. In the case that the other binary files are needed to be loaded to the CPU memory, the target download functionality of the loader controller can be used with the script. In this case, target download on the fly without any reset needed is executed. This method doesn't change the WinIDEA configuration. Verified download method of the loader controller is also quite often used. In the case that you would like to change the list in configuration of the WinIDEA session with a script, you can use the add to download list and remove from download list methods of the loader controller. I will demonstrate that. Let me change to the demonstration. I'm back to WinIDEA session for the Cortex-M CPU. Let's check what are the download files. So I'll open debug files for download, and here's my list of the binaries to be downloaded. Currently I have just one member, output.elf. It is an elf file, and I have defined here code and symbols offset. Okay, let's close the windows, and now I will open the script. The script that will add additional file to the download list. At the beginning, a loader is created here. this line, and then this function add file for download will add additional download file. The download file is sample.elf. It is a elf type file, and the code and symbol offset is 0. Let's run the script. Okay, first the script printed out what is on the list. It's just output elf file, and then additional one file sample elf is added to the list. Okay, let's check. Let's go back to the definition of the WinIDEA. So now I have additional one sample elf file. Let's remove it. I don't need it. Maybe we can also check another features of the script. I also created IDE controller, and I immediately used IDE controller and print out the WinIDEA version. So at the beginning, WinIDEA version matches the isystem.connect SDK. Then I have additional function that will go and print out all the details of the list of the download files. For that I used so-called uh, display options. Display options basically can configure all the WinIDEA settings. I can access them here, display options, and then I can display it. Basically every setting inside the WinIDEA has so-called display options, and we can modify it with the IDE controller. But for now, let's leave this feature, and I will explain this next time. I will describe some examples of functionality of the IDE controller. IDE controller is used for resizing windows, saving and closing documents, closing WinIDEA views, reading out the WinIDEA version information, changing most of WinIDEA settings on the fly. The changes are provided through the direct API functions or by changing so-called WinIDEA display options. With the data controller, you can evaluate and modify variables, CPU registers, special function registers, raw memory, and C expressions. Most modern CPU support real-time data access. It is important to check if real-time access is enabled in the WinIDEA configuration. Memory access can be performed when the CPU execution is stopped. This is so-called monitor data access. Usually, a CPU uses different hardware feature for each of the data accesses. It is important to use the right flag. This is monitor or real-time access flag for each access case. Now, I will demonstrate some data accesses example scripts. First, I will demonstrate a short script that will read out some global variables in real time. So the flag f real time will be used. The variable test1 will be written with the value 200, and immediately it will be read out whether this change was successful. Then the global variable will be read out. Then the C expression will be checked. If the G count 1 is equal to G count 2, the result of this C expression will be immediately stored in variable compare, and if compare will have value 1, it means that this C expression is true, otherwise it will contain 0, meaning the C expression is false. Then in some lines we will write a value into the raw memory, and immediately it will be read out. This value will be 4321. Then the execution will be stopped and the stack pointer value will be read out. So let us run this script. Now the script start to execute. In this line, the write of 200 into variable test val was successful. This is the float variable. Then the C expression is false. Here it is written into the raw memory, and the last value is a stack pointer value. So for the stack pointer value, a at should be appended before the name of the register. So stack pointer for the cortex is R13, and at is meaning accessing the register value. Next, I will present a script that will profile a function. It's so-called performance counter measurement. The script will measure what times and how many cycle counts will take the execution of the test point function. So the accesses of so-called DVT performance counter will be accessed and modified with a script like this. Here it is written, for instance, DVT performance counter is enabled, and at the end the counts will be displayed. So let's start with the script. It will start execution and it will measure. So these are the raw registers, this is the count number, and the time. It took over 339 microseconds. Okay. So the third script that I will demonstrate, it's a data recorder. The script will record two variables, I counter and G counter. It will measure for 10 seconds and it will sample the values every 0.2 seconds. So let's start. And the script is starting to sample in exact times, and the values will be displayed. At the end, the script also stores the results into the Excel table. Address controller provides information about symbols and source code. For instance, you can get addresses of variables, functions, and labels in a RAM and in a flash memory. You can get addresses of a source line, for instance, when searching the right line to set a breakpoint. You can get a symbol at a given memory address. Also, you can get an address of an expression. So, I will switch to demonstration. So, let's open the example script for the address controller. This script will print out the location of the main function in flash, then the location of G counter 1 inside the RAM, then it will find the location of the element of the structure, and it will be this address will be displayed. Then the debug symbols will be used to read out what is the size of the structure, what is the exact address, and where is this area located. Then the complete structure will be initialized with a 0. So the idea is to use debug symbols. Even if we have a new version of the build, we can still figure out what is the new size of the structure. We are still able to initialize the complete structure, even if there are new members of the structure added. So let's run the script. So these are the addresses of the main. I can show. It's E24. So it's E24, the location of the variable, location of the element of the structure. Then the structure engine is displayed, the size, the address, and before the initialization these two members of the structure contain certain value, but after the initialization the values were cleared. So these are the elements of the structure, and the lines where the structure is initialized are these here, because the script automatically figure out what is the address and the size from the debug symbol information. isystem.connect API includes the stack frame analysis. A call hierarchy, local variables, and its values are determined for each call context. I will go to demonstration. So first I will open the script. The script is called stack frames. This script will run until the function temperature sensor read, and there will print out the local variables and also the function names of the call stack. So let's run the script. Okay, the script has stopped, and here we see the same as it is presented in the Win idea: reset, main, temperature read, the local call stack. Yeah. And also the local variables are presented like here: ID, inside the function temperature sensor read, and so on. With the execution controller, you control the execution of the embedded application on the target. You have possibility to execute run, run until address. These methods are non-blocking. You are familiar with the wait until stop method that is used for checking if the execution has terminated or not. The other method is wait until running. There is additional variant for the execution methods with a timeout. The timeout could raise a timeout exception in the case that run method didn't terminate on time, or it could return certain error value. The other typical execution methods are: step high is stepping on a source code. Step instruction is on a binary level. There are also goTo function and goTo address. You can completely change the execution by using them, but you need to be careful not to crash the stack. An embedded function could be called directly from Python. Again, you need to push on stack the function attributes before calling the function. These methods are blocking. As the name implies, the breakpoint controller controls breakpoints on the target. Breakpoints could be enabled, disabled, set, cleared. There is possibility to use hardware or software breakpoints. The sample code presents the simple use of setting a breakpoint at the beginning of the function findMax. I will use execution and breakpoint controller for creating a fault injection script for the function tempRead. This function calls sensor read from getting the temperature from an engine. If the temperature readout from the sensor is too high, an alarm is raised by setting a galarm variable. Fault injection script will change the temperature readout from the sensor in order to raise the alarm. First part of Python snippet searches the line with if statement inside the function temperature read. When the line of the if statement is returned, a breakpoint is set. Then the execution is continued until the breakpoint is hit. The value of the temp variable is modified to 101. After that, two steps on the source level are executed and the alarm is set. The value of GAlarm is printed out. Let's go to demonstration. I will open the fault injection script. Okay. The script searches for the line if temperature read and then change the value of the temperature to 101. So let's run the example script. And here we are. The GAlarm is raised and the breakpoint is set here on that line. The coverage controller to execute the coverage measurement. First, a configuration of coverage measurement is set, then a coverage is measured. In the end, the coverage measurement results are exported. The class coverage data to provide access to coverage data exported to XML file. After parsing the XML file, the coverage information is displayed. I will demonstrate an example of coverage measurement script. So I will open the script first. The script name is coverage to example, and at the beginning the TRD file for the trace analyzer is defined, and then the scope of coverage measurement for the first case is all the downloaded code. Then the coverage will start, the execution will run, and then after 3 seconds the execution will be stopped and the coverage will be stopped, and then the measurement results will be downloaded to WinIDR. We need to wait until this is finished, and then coverage measurement will be exported to XML file, and the second time it will be exported to HTML file, and then the second time we will measure 4 functions, temperature, read, and so on, and results will be also exported, but also the script will print out directly the coverage measurement results. So let's start the script. The trace analyzer is running, it's recording, and the results are now being downloaded, and then the export will start it. So export is operating right now. Then the second time also the HTML will it's been recorded already. Then the second coverage measurement is executing. Now it's stopped and the results for the 4 functions are printed out. We see which line has been executed and not, how many branches were executed and not, and so on. So I will close the script now and I will proceed with the HTML file. So let's open the coverage HTML report. I can use a browser now. So here I have my models that were measured with the coverage. I can browse all together. I can click on the functions and I can see what source line has been measured with the coverage and which one haven't been executed and measured with the coverage. So this is very useful, for instance, for continuous integration, for testing, where you can see what was tested and what not. This slide displays most commonly used isystem.connect controllers. These are connection manager, execution controller, trace controller, breakpoint controller, loader controller, data controller, IDE controller, and coverage and profiler controllers. Some frequently used methods of the classes are displayed too, but isystem.connect API has much more classes and methods available for the automation of several use cases. On the iSystem web page is extensive documentation of isystem.connect API. You can find a documentation of classes and controllers there. There are also many example scripts. Link is provided on this slide. I will show some bits of online documentation. I will open controllers. Here are many controllers. I will select, for instance, debug facade. You see, the method of the debug facade is really extensive. So I can click write memory and the additional documentation will be displayed. I can select the input attributes and this will provide me further information. So let's go back to the top. Here I will open examples. There is documentation of many example scripts. Let's open, for instance, read target variable. So here is an example. I can directly copy it, modify it, and create a new Python file for my use case. This is the fastest way how to proceed with the scripting. At the end, I would like to mention that you can find on iSystem webpage many additional help, documentation and trainings on how to prepare test idea testing, on debugging with WinIDEA and how to start tracing with the iSystem tools. Now, I will finish my presentation and I will give back the word to Sabrina. Sabrina?
Thank you, Aleš, for your presentation. And as already mentioned at the very beginning, now it's time for some questions for you. One is, what Python versions are supported by the isystem.connect API?
Okay. Currently, with the last WinIDEA versions, we support Python 3.6 to Python 3.9. But we also support the oldest not supported by Python versions like 3.3 or 3. Up to the 3.5. But on request, if you ask for certain older versions of Python, we can also create SDK for that.
Do we recommend one version or should customers always use the newest version? Any
We
advice
recommend
here?
Okay, sorry. We recommend to use the versions that are supported by Python. Currently, this is 3.6 up to 3.9. These versions are maintained for the bugs, and we support to use them. I would recommend that you use them.
Okay. Another question is, can we control the stack usage with a script?
Yes, sure. The idea is as following. For instance, for the bare metal application, you can get the information of the stack start or stack end within the debug symbols. And then after the first initialization of the RAM, you immediately stop and then you, with the script, access the chunk of the memory that is used by stack, and you can initialize this with a data controller with a certain pattern. Then you can run the application, and then you can at certain moment stop the execution, check the current stack pointer, and then you can search up to certain level up to what certain level the pattern was rewritten with the values during the application. And then you can detect up to what level the stack was used. For instance, for the second use case would be for the using the real-time operating system. Then most of the time the operating system already has per stack the variables that controls the stack usage. You can simply read out them. This would be the simplest way.
Okay, thank you. Aleš, another question is there a difference in the call stack feature when you use WinIDEA ID directly or when you use it via scripting?
No, it's the same. With the script, we just read out replicate the same functionality as it is implemented by the WinIDEA, but basically we got the same information always.
Okay. Then another one came in, is the use of the API also validated for functional safety tests according ISO 26262?
Directly not. Because we have so many WinIDEA versions, we don't immediately, we don't stamp it with and we don't ask and get approved for the standard. But on request, we can help customers how to proceed with getting this approval for the standard.
Yeah, I think this is also a big topic which should also discussed offline. So if you are interested in learning more about functional safety development with our tools according to some standards as ISO 26262, please reach out to your contacts and then we can go on discussing this in more detail, also according to your development strategy. Let's take another one. We have some more minutes left. Can we merge several coverage measurements with a script into one coverage report?
Yes. On our web page, there is example script how to proceed and how to implement this. The fastest way is that you just reuse this prepared example script from our web page. And yes, you can do this.
Thank you. Let's pick the next one. Can we control WinIDEA using external software or only via scripts?
Can WinIDEA control external software? If we have debug symbols, loaded to WinIDEA to debugger, then the debugger could know what are the variables and etc. So basically, you can control this then with the WinIDEA or with a script. Hopefully, I understand right. What do you mean external?
Yeah, I also understood it like this. So you can remote control WinIDEA with scripts, right, Aleš, with
Yes.
Python, for example, and this is how the approach is working.
Yes.
Let me just check. There are a lot of questions coming in, so we are running out of time. We can definitely not answer all questions, so we will reach out to you again. And can customize library functions? No, sorry. Can we customize library functions as per required in the parameter settings?
The API already has fixed structure, but you can reuse it. It's very extensive functionality, and you can, enhance what you need from it. So you can use basic the base functions, and then you implement your own API if you need a different approach. We provide really huge list. The best idea is that you ask support or me how to, and I can help you and assist you how to be the most effective, what is the most effective usage of that APIs.
But you can also adjust the scripts to your use case, right? When you're using the examples, you can adjust them.
You always need to adjust them to a certain level because the values of variables, memory chunks, etc. differs from the application to application. And of course, you just, from examples, you can see the ideas and then you can reuse those ideas, those lines, and you modify the variable names, etc. Of course.
Okay, then let's pick a last one. Can we run a parallel execution of one script on several different remote machines, given that we point the exact versions and IP addresses?
Okay, you can run in one script parallel several connections. Of course, all debuggers and WinIDS sessions must be the same version. Yeah? Then you can handle this with one script, and this is just an interface, and then you can connect to exact project, and you create an instance for with the connection manager and all other instances for that debugger, and then you create another connection instances to connect another debugger. Yeah, so sure, you can do this.
So it's a very powerful tool. A lot of things are possible. And
Yes.
let's come to an end for this episode. All questions which we have not answered now will of course be answered by email afterwards, and we will reach out to you and for further discussion. But before you leave, don't forget to download the webinar presentation in the handout tab. Feel free to test our online test idea tutorial on our webpage. Check out our YouTube channel. This webinar will be hosted there. A lot of others are already there. And if you want to get updates automatically, feel free to register to our newsletter. Then you will also get the invites for our upcoming webinars. If you have questions later after this webinar, please send us an email to webinar@isystem.com or reach directly out to your sales or tech representative at iSystem. So thank you for attending. We would be happy if you fill in the feedback form before you leave, and have a nice day, have a nice evening. Bye and take care.